Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the class. So today we will discuss about the higher order cycloaddition reactions. In the previous classes, what we have discussed is about the 2 pi plus 2 pi cycloaddition reactions. On the other hand, 4 pi plus 2 pi cycloaddition reactions, which are also called as Diels-Alder reaction, right? So 2 pi plus 2 pi supra cycloaddition reactions are photochemically allowed, and 4 pi supra plus 2 pi supra cycloaddition reactions, that is the Diels-Alder reactions, are thermally allowed reactions. So besides these two important cycloaddition reactions, there are little more types of cycloaddition reactions which involve more than 6 pi electrons in the cycloadditions. So when they are adding with each other. So they are 4 pi plus 4 pi cycloaddition reactions, 6 pi plus 2 pi cycloaddition reactions, and 8 pi plus 2 pi cycloaddition reactions, as well as 14 pi plus 2 pi cycloaddition reactions. In all these cases, if you observe, each partner is giving, in the case of 4 pi plus 4 pi cycloaddition reactions, 4 plus 4 pi electrons, together 8 pi electrons are involved in the reaction. Whereas in the second case, that is the 6 pi plus 2 pi cycloaddition reactions, the first partner is giving 6 electrons and the second partner is giving 2 pi electrons, together 8 pi electrons. In the third type, 8 pi plus 2 pi, 8 plus 2, 10 pi electrons are being involved. So, and in the last type, 14 pi plus 2 pi cycloaddition reactions, again 14 plus 2, 16 electrons are involved in the cycloaddition reactions. So, any cycloaddition reaction which is involving more than 6 pi electrons in it during the cycloaddition process is treated as higher order cycloaddition reactions. So, according to the Woodward-Hoffmann rule, so what Woodward-Hoffmann rule was predicting is that 4n pi electron systems are there and 4n plus 2 pi electron systems are there, right? So 4n pi electron systems means either it should involve 4 number of pi electrons, or 8 pi electrons, or 12 pi electrons, or 16 pi electrons, like this. And 4n plus 2 pi cycloaddition reactions means it should involve either 6 pi electrons or 10 pi electrons, 14 pi electrons, 18 pi electrons, like this. So if you see this, 2 pi plus 2 pi systems together is contributing 4 number of pi electrons. So therefore, these 4n systems are photochemically allowed. So these 4n pi electron systems are photochemically allowed according to the Woodward-Hoffmann rule under cycloaddition conditions. Whereas this 4n plus 2 pi systems will show thermally allowed cycloaddition reactions. So for 8 pi electrons, 4 pi plus 4 pi cycloaddition reactions will be photochemically allowed, right? So 14 pi plus 2 pi cycloaddition reactions should be photochemically allowed. On the other hand, if you see here, the 6 pi electrons means 4 pi plus 2 pi cycloadditions, which is also called as Diels-Alder reactions. And then what you will be seeing is 8 pi plus 2 pi cycloaddition reactions, so which are nothing but 10 electrons they are contributing. So it is also thermally allowed reaction. And then before that, 6 pi plus 4 pi is also thermally allowed reaction, okay. So please just try to see this Woodward-Hoffmann rules and which are allowed under which conditions. At the end, we will have a surprise, right. So, what is that surprise means? The 14 pi plus 2 pi electron system, which should be generally under supra mode, photochemically allowed, will be seen as a thermally allowed reaction, will be seen as thermally allowed reaction. So, in the thermal conditions, the 14 pi partner will act as the antera partner and the 2 pi partner will act as the supra partner. So, in detail we will discuss about this in the later part of this class. So, higher order cycloaddition reactions. In that, we will see first this 4 pi plus 4 pi cycloaddition reactions. So, these 4 pi plus 4 pi cycloaddition reactions are photochemically allowed. They are allowed according to the Woodward-Hoffmann rules. Okay. So, there are certain examples which can be studied under 4 pi plus 4 pi cycloaddition reactions. They are as follows. So, if you have a naphthalene molecule, so naphthalene molecule, this is the naphthalene, and if the double bond which is at 9th and 10th carbon atom, 9 and 10 position is removed and you have hydrogens here. We call this as 9, 10 dihydro naphthalene. So, this 9, 10 dihydronaphthalene molecule upon irradiation, so this is photochemically allowed. So, therefore, to perform the cycloaddition reaction you have to irradiate. So, you have to irradiate it with a particular wavelength of light, that is 254 nanometers, and this reaction happens at very low temperatures at around minus 110 degrees centigrade in the presence of the solvent THF D8. Okay. So, these are the reaction conditions you need to provide. In this particular type of reaction conditions, the dihydronaphthalene undergoes 4 pi plus 4 pi cycloaddition reactions. What is this? This undergoes 4 pi supra plus 4 pi supra cycloaddition reactions under these particular conditions. So, the portion acts as an individual 4 pi partner and this portion also acts as an individual 4 pi partner. So, the product will be like this. What you are going to see after cycloaddition is like this, right. So, it gives the product like this. So, coming to another example, that is the cycloaddition of anthracene molecule, which can also be called as dimerization of anthracene molecule, right. So, the reactive carbon atoms are these center carbon atoms. So, this is anthracene. Upon irradiation, it also undergoes 4 pi supra plus 4 pi supra cycloaddition reaction and gives you a dimer. This is the dimer formed upon the 4 pi plus 4 pi cycloaddition of anthracene molecule. So, this anthracene is not substituted at this center carbon atoms. what happens if you give a substitution? 9 substituted anthracene if you take. That means if you put any substituent at the 9th position of this particular anthracene molecule, upon cycloaddition reaction, you will get two different types of isomers. That is head to head type of dimer and head to tail type of dimer. Head to head means the two substituents on the two anthracene molecules upon after cycloaddition reaction will face in the same direction, right? Will protrude towards the same direction. So whereas in the head to tail type, so one substituent of the one anthracene molecule will be facing in the different direction and the other will be facing in the other direction, right? So you will get two different isomers. One is the head to head and the other is the head to tail type of isomer. So you see that. So this is head to head dimer, and this particular dimer will be seen if the reaction is performed in non-polar solvent. Okay. So similarly, you will be able to see the head to tail dimer, like this. So the head to tail dimer will be seen when the reaction is performed under polar solvents. Okay. So this is the case with the 4 pi plus 4 pi cycloaddition reactions. Another example for the head to head dimer formation or head to tail dimer formation with respect to pyranones is as follows. So dimethyl pyranone upon four pi plus 4 pi cycloaddition reaction under suitable condition will give you two different types of isomers. Like this. Double bond O. Yeah. So this is head to tail isomer, and similarly so these two types of isomers are formed upon irradiation of this particular molecule, which undergoes 4 pi plus 4 pi cycloaddition reaction. So what happens if there is no substituent? So this undergoes the cycloaddition reaction, giving you so upon cycloaddition of this molecule, you will be seeing this. So this is a head to tail type of arrangement, which is centrosymmetric in nature. Okay. So now coming to the 6 pi plus 4 pi cycloaddition reactions. So, the 6 pi plus 4 pi cycloaddition reactions, where the first partner is contributing the 6 pi electrons and the second partner is able to contribute 4 pi electrons, we will see. According to the Woodward-Hoffman selection rules, so the 6 pi plus 4 pi cycloaddition reactions are thermally allowed. That means 6 pi sopra plus 4 pi sopra cycloaddition reactions are thermally allowed cycloaddition reactions. There is one particular example which we need to concentrate or which we need to give certain amount of importance, is the reaction between tropone with cyclopentadiene molecule. So, the tropone molecule acts as the 6 pi electron partner, whereas the cyclopentadiene acts as the 4 pi electron partner. Okay. So, the reaction between these two will be somewhat interesting to note. We will see that. The cyclopentadiene upon reaction with this tropone molecule under thermal conditions, this cyclopentadiene acts as the 4 pi partner and this acts as the 6 pi electron partner. Okay. So, it is subjected to 6 pi supra plus 4 pi supra cycloaddition reaction. So, you have a better chance of observing here that any conjugated system which is connected to an electron withdrawing group will provide you such an opportunity to see the endoisomer as well as the exoisomer. And according to the Alder's endo rule, which we have discussed in the previous class, so the endoisomer predominates under such kind of conditions because the molecule is capable of establishing the secondary orbital interactions besides the primary orbital interactions which are responsible for the formation of the sigma bonds. The secondary orbital interactions formed in the cyclic transition state will stabilize the cyclic transition state to a greater extent, which therefore give you the kinetic product, that is the endo product, as the major product, right, at low temperatures. So, in this particular case, you will not be seeing any type of endo product, that is the percentage of endo product is absolutely 0, whereas the exo product only predominates. So, 100% of exo product can be seen in this particular example. Why? What is the reason? Why this tropone molecule is not capable of establishing the fruitful or the positive secondary orbital interactions? Why this is leading to a repulsive secondary orbital interactions with respect to this tropone molecule? We will see with the help of the frontier molecular orbital theory. So, this is the cyclopentadiene part which has added to the tropone molecule, and you will see the exo product as the only product. So, that means 100% of the exo product. So, this particular tropone molecule, as it is acting as the 6 pi electron center or partner, it utilizes all these 3 pi electrons to be involved in the cyclic transition state during the addition reaction. So, this is the first carbon atom, second, third, 4, 5, 6 and 7. So, instead of acting as a simple dienophile and participating in the 4 pi plus 2 pi cycloaddition reaction, that is the Diels-Alder reaction, this molecule chooses to be a 6 pi electron partner and participates in the 6 pi plus 4 pi cycloaddition reaction. This particular phenomena is called as periselectivity. This phenomena is called as periselectivity. Why this is participating as a 6 pi electron partner instead of a 2 pi electron partner and facilitate the 4 pi plus 2 pi, that is the Diels-Alder reaction. So, means the coefficients of the molecular orbitals, the coefficients of the molecular orbitals of LUMO molecular orbital in the tropone molecule is found maximum at C2 and C7 carbon atoms. So, the coefficients of these particular molecular orbitals are found maximum at the C2 and C7 carbon atoms, which makes them to participate in the bond formation during the cycloaddition reaction. Okay. So, that is one reason. So, that is also the reason for making this as a 6pi electron partner, and this phenomena is termed as periselectivity. So, coming to the molecular orbitals of this particular partners and see why the exo product predominates over the endo product. In the normal type of approach, that is like in the endo approach or in the exo approach, how the tropone molecule is approaching the cyclopentadiene, we will see, right. So, cyclopentadiene so this is the diene molecule and these are the pi molecular orbitals. So, it uses the homomolecular orbital and psi2 is the homomolecular orbital for this one, right. So, how the psi2 molecular orbital will look like? It has one node. So, at C1 and C2 plus plus and minus minus will be seen at the C3 and C4, right. So, this is the case. So, how the tropone approaches this cyclopentadiene is only matters. So, tropone has 3 pi bonds and psi4 acts as the LUMO molecular orbital, double bond O. So, psi4 means there are 3 nodes starting here, one node is present in between these two. Yeah, one node is here, second node is here and third node is here. So, 3 nodes are seen for this psi4 molecular orbital. So, now there is a fruitful primary orbital interaction in the cyclic transition state, which produces the exo product, right. And if you want to see the same molecule so as to justify why it is not giving the endo product, okay. So, again do the same. So, this is the psi2 molecular orbital and this is the psi4 molecular orbital, this is LUMO and this is HOMO. So, now we will see how the secondary orbital interactions. So, primary orbital interactions are happening here with the C2 and C7 because their coefficients are the largest, and this is the primary orbital interaction. Coming to the secondary orbital interaction, if you see this, this is the positive lobe and this is interacting with these molecular orbitals with negative lobe, and at the same time, so this is interacting with this one. If you clearly observe these secondary orbital interactions, so they are repulsive in nature. So that is why it avoids the approach of the tropone molecule in the endo form. So endo approach, this is called as endo approach, and it results in the repulsive secondary orbital interactions which destabilizes the transition state of this endo isomer, right. So this is the exo approach, and you will see only the exo product in this particular case. Yeah. So now we will see the 8 pi plus 2 pi cycloaddition reactions. So according to the Woodward-Hoffmann rule, this 8 pi plus 2 pi cycloaddition reactions are also thermally allowed reactions. Okay. Similar to that of the 6 pi plus 4 pi cycloadditions, 8 pi plus 2 pi is also thermally allowed cycloaddition reaction. So some of the examples are like the reaction of indolysine. So this is indolysine molecule. Upon treating it with dimethyl acetylene carboxylate, this indolysine acts as the 8 pi partner, and this acetylene derivative acts as the 2 pi electron partner. So what happens here is, the cycloaddition reaction takes place. Under thermal conditions, 8 pi sopra plus 2 pi sopra cycloaddition takes place, resulting in the formation of the product. This and this, COOCH3, hydrogens here are cis to each other. So this is the one of the example for 8 pi plus 2 pi cycloaddition reactions, and another example can be seen as so this also acts as the 8 pi electron partner, and this acts as 2 pi electron partner. So upon cycloaddition, you will be able to see this bicyclic molecule. These two are the new sigma bonds formed. And this is the product, right. So there may be some other examples, and you can work out some more examples. So the last one is 14 pi plus 2 pi cycloaddition reactions. As per the discussion in the beginning of the class, this 14 pi plus 2 pi cycloaddition reactions, if it has to be performed in supra mode, this is photochemically allowed. but in general the 14 pi partner acts as the Antara partner and the reaction happens under thermal conditions. The 14 pi Antara and 2 pi supra cycloaddition reactions are thermally allowed according to the Woodward-Hoffman rules. Okay. So, we have an example for that. This one, all the bonds are in conjugation, right. So, and now this as a whole acts as a 14 pi partner. If this particular molecule is made to react with tetracyanoethylene TCNE, this is TCNE, which is a 2 pi partner. So, the reaction flows in this way. Under thermal condition, the 14 pi partner acts as the Antara partner and the 2 pi partner acts as the supra partner, and the reaction happens like this. Okay. So, this particular reaction was successfully established and proved, and the product is also isolated, and the single crystal data is also available for this particular product, cycloaddition product. From that data, what is observed here is the hydrogens present at the junction of the rings is trans in nature, they are opposite to each other, right. Why this is happening means the 14 pi partner acts as the Antara partner. So, this bulky molecule cannot stay in the same plane and it flips to some extent. So, which allows the 2 pi partner to approach it in the manner such that the Antara position of the 14 pi electron system is more feasible or more approachable for the cycloaddition reaction. So, therefore, it shows the product where the hydrogens at the junction of the rings is in the trans position. So, this is one of the exceptional case which you can see in the 14 pi plus 2 pi cycloaddition reactions. Okay. Thank you.